Alright, so we did the light work. The light work was not bad, but now it's really time to get down on the algebra. This is where your Algebra 1, Algebra 2 business really comes into play, because we got to start rearranging stuff. It's almost like chemistry. You can rearrange molecules and you get different molecules rearranged, like the elements where they bond. I hate chemistry, but it's kind of like chemistry, right? So let's talk about a few things before we do our problem, and then we'll get rolling. So first thing, inelastic collision. So we just did elastic collisions, where everything is 100% conserved, all the energy. Inelastic collision, as we see here, in which objects collide and some mechanical energy is transformed into heat. This is like real world collisions. You know, if you smash two metal ball bearings together, they're going to make a little bit of heat. And hopefully you've probably done that experiment already, and you saw that it makes a little bit of heat because you can smell burning paper, right? So let's talk about this equation that we've been working with. Let's talk about how it can look, the different ways it can look, okay? Before we get rolling. So, first off, this is the original way it looks. Mass volume plus mass volume. So when we're dealing with two objects, the momentum is momentum of one object, mass times volume, mass times initial velocity, mass times initial velocity should equal mass times final velocity, mass times final velocity, right? Let's look at all the ways this can be written, even though it's the same. Because remember, algebra, you can rearrange stuff as long as you're equal on both sides. So we also know momentum equals momentum, initial equals final, and momentum is mass times velocity, right? So let's look at way number 2 we can write this. We can write it like this. Mass times initial velocity plus mass times initial velocity equals, and since we kind of do that substitution, we can open parentheses, mass of one plus mass of the other, and then times final velocity, because we know this would substitute, right, or multiply in. So this is the same. This is the same as this, rearranged. Let's look at another way we can write this, and I'm going to add some steps so I can show you how we got this. Ooh, I forgot to do this. There we go. Mass initial velocity plus mass times initial velocity equals, so we have mass times final velocity plus mass times final velocity. So right now I'm going to add something in here. This is mass of first object, this is mass of second object, first object, second object. So that's all this one means. First object, second object. There we go. So now let's algebra this, right? So what we can do is we can subtract this over, minus mass of first object times the final velocity, which cancels this, right? Minus mass of first object times final velocity. So now we have this. We have mass of object 1 times the initial velocity plus mass of object 2 times initial velocity minus, notice we have this now, mass of object 1 times the final velocity. And then we have equals mass of object 2 times the final velocity. We're not done though, because we want to get 1 by itself. And now remember, now this is multiplying, right? So what we can do to make it go away is we can divide by mass of object 2. That cancels, which means this is now divided by mass of object 2. Now we're going to flip it because we like it in good order. So the third way is going to look like this. The final velocity equals the mass of object 1 times the initial velocity plus the mass of object 2 times the initial velocity minus the mass of object 1 times the final velocity over mass of object 2. So that is shown here, right? It's the same thing. So now that we got that, let's try to solve it. So let's look how they did it here. Mass of object 1 goes here, times the velocity of object 1 here, plus, so I'm going to fold this so we can kind of see what we're doing here. So mass of object 1 goes here. Velocity of object 1, velocity is here, so one object, initial velocity 10. 300 times 10, so that's why that says 3,000. Plus the mass of object 2, which is 125, times the velocity of object 2, which is 0. So we know this is going to end up being 0. Minus the mass of object 1, 300, so 300 was there, times the final velocity, which is 412. Final velocity here. And let's see. Divided by mass of object 2, 125. Now, for these, because they're inelastic, both objects have a velocity instead of having like the same kind of velocity. So in this case, this one here is going to be the velocity of, what is that? Object 1. The final velocity of object 1, and what we divided over here was the final velocity of object 2. Does that make sense? So up here, when it was the mass of object 1 times the final velocity of object 1, now in these equations we're dealing with the final velocity of object 1 and 2 because they'll have different velocities. So now that we got that, let's see if we can solve one of these. So we'll go to the next page. This is just my notes from another one. And let's give it a shot. Let's go to number 7. If I can find it. There we go. So, let's highlight what we need to know. And we're going to use this one. So, highlight first. Things I see important. Blah, 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 blah. There's a ball. Weighs this much. Has this velocity. And then it's hitting a bottle that weighs this much, sitting on a shelf. When it makes contact with the bottle, it goes flying forward at this. What is the velocity of the ball after it hits the bottle? Here we go. So that's the first question. So first thing we do is we'll always write our formula. We're going to skip a few formulas because you guys have been doing this a while. So hopefully you get it by now. So that being said, let's write our formula. Mass of object 1 times the initial velocity of the object, right? Plus mass of volume 2 times the initial velocity of the object equals mass of volume 1 times the final velocity of the first object plus mass object 2 plus the second of object 2's final velocity. I know it's a lot of stuff. It's like a mouthful, right? So here we go. Let's plug it in. So we have the first velocity of object 1, which is the ball, right? Because we have the ball and then we have the bottle. So the first velocity or mass is 0.5. And we know that's going to be times 21 because the velocity is 21 meters per second. So 0.5 kilograms, units real small, times 21 meters per second plus mass of the second object, which is 0.2 kilograms. 0.2 kilograms times the velocity of the second object, the initial velocity of the second object, right? Which was 0 because before the bottle got hit, the initial velocity was 0, right? Equals, all right, we're still going. The first mass, the mass of the first object times the final velocity of the first object, which we don't know because we're trying to find the velocity of the ball after, right? So we don't know the velocity of this object after it started flying, right? Plus, now we're doing this side, the mass of the second one, 0.2 kilograms, times, we know the final velocity of the bottle, right? That was 30. So times 30 meters per second. Whew, it's a lot of stuff, guys. We got to take it step by step, day by day. Something, hey, hey, hey. I don't know. That was a 90s show. It was pretty good. I think it was called Step by Step. All right, let me see the calculator. Awesome. So first I'm going to go 0.5 times 21, and that's going to be 10.5. So we're going to drop that down right here. 10.5 equals the momentum of the, this is the ball, right? So this is the ball. This is the bottle. This is my bottle here. Cool. Plus, now we got to do this. We know blah, 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 blah. That's just 0, right? So I don't care about that. So that's 0. Equals. So I'm going to bring it down again just to get the left side ready. 10.5 equals. Now, we have 0.5 times the final velocity of the first object, which we don't know. And the first object is what? The ball, right? So that's going to be my ball. Plus 0.2 times 30. So, erase all that. 0.2 times 30. Bam, 6. So that's an easy one, right? Plus 6. Now that we got this, let's rewrite it. 0.5 final velocity of object 1. Object 1's final velocity plus 6. There we go. So now what we got to do, it's plus 6. We got to make the 6 disappear. So we're going to go minus 6. Minus 6. So 10.5 minus 6, let's just be safe. I'm going in a safe mood. 10.5 minus 6. So 10.5 minus 6. 4.5. Awesome. So 4.5, we still see, equals 0.5, the first object's final velocity. So times the first object's final velocity. Now, how do we do this? Remember we divided out, right? So divide by 0.5, gone. Divide by 0.5. So I'm going to flip it, right? Just because I like the letter to be on the left. So I'm going to go the first object's final velocity equals, so 4.5 divided by 5. Divided by, no, stop doing this. 0.5 divided by 5. 0.9. Did I do that right? 0.9. 4.5 divided by 5. 0.9. 0.9. Okay, so correction. I messed this up. Scratch this. We're close though. So we're close. So I think I typed this in wrong. Y'all probably already saw it on video though. 4.5 divided by 0.5. 9. Okay, that's much better. So scratch this. So the first object's final velocity, so the first object was the ball, right? Final velocity equals 9 meters per second. So let's scroll down and see what the second part of the question was. So answer A, what is the velocity of the ball after it hits the bottle? So that was the final velocity of the first object, and we said it was 9 meters per second. Answer B, if the ball were more massive, how would this affect the final velocity of the ball? Well, remember, if the ball were more massive, let's look back at our formulas. So we're going to check it. So the question was, if the ball were more massive, how would it affect the final velocity if it was more massive? So if the ball was more massive, so let's look what we did here. At the end of our equation, we had to do 0.5, which was, remember, the mass of the ball. We had to divide that over, and that was the final velocity of the ball. If the ball were more massive, let's say the ball was, let's say 2 kilograms instead of 0.5. So then, in that case, I'm going to put it on the side because this is like parallel dimension, right? Then we were at 4.5 equals, how did I say, 2 kilograms times the final velocity of object 1. So pretending that the ball was 2 kilograms instead of 4.5. Then we got to divide out the 2. Then we got to divide by 2. So that's 4.5. Daughter there. So that's 4.5 divided by 2 now in our like alternative dimension, right? So now it's 2.25. So now we'd be saying the final velocity of the ball equals 2.25. So in this case, our answer would be the final velocity would actually be smaller. So if the ball was more massive, the final velocity would be smaller. Make sense? So right here, you'd be like, yo, if the ball was more massive, The final